Okay, so in the chapter 11, 11.5 lectures, Tom basically talks about the idea of exponential growth and decay. And so um, you to evaluate the word problems given for the exponential growth and decay, you're able to come up with some sort of formula to be able to graph and show basically the rate of change. And so in this situation, he says that the rate of change, the word problems at the rate of change in a bacon count is proportional to its balance. So based on the rate of change, you're able to um, well, okay, let me be more clear with this. So the formula actually comes from God, where is it? Scroll down. Okay, well, right there, right there. So our associated equation is the change of rate equals the constant times the p, which is p is um, the it's just a variable. It's just right. It's just a variable that you're trying to apply. And so once you have this initial change of rate function, you're able to find exactly what your initial, because your intention is to find the starting balance. And to be able to find that, you use this formula to be able to go in that manner. And so right now you're just gonna use separation of variables to find to separate the variables. And essentially you can integrate them after you separate them. And after this doesn't really tell you anything. It's not really beneficial. And so you would have you want to find what the b value is exactly. And so you would take the log of this function, and then or the natural log, and then it becomes this. And then so like this e function, you can rewrite it in a manner where you can rewrite it like this. And so it becomes this. But the thing is that the e to the c is essentially a finite number, so it's a constant. So you can essentially replace it with just a general variable, in which you replaces it with bo, and so that's a constant that you have. And from there, you can essentially plug in because you want to find a starting balance at t equals 0. And so you plug in your numbers, and you find out that so the initial value of your balance is 100. And from there, you can find out this next function shows you that this is the rate of change of, you can find a balance with this rate of change. And so, but what's particular about this function, this problem is that this is a exponential growth, and this is because the initial rate of change is positive. And so for exponential decay, the rate of change would be negative. And so in this problem, he goes over this. And so now we come up with we have a new word problem, and with cookies and room, and temperature of the cookies once in an oven, and the temperature of the room outside. And essentially using the Newton's law of cooling, you know that the rate of change of the temperature of the object is proportional to the difference in temperature. And so rate of change equals the change in temperature. So 100 H is essentially 170. We don't know that yet. We just know that the H represents the original temperature, and 70 is the final value. So that is the change of temperature that they use based on Newton's law of cooling to be able to find the rate of change. And so K is just a constant that basically is more of a additional factor to be able to further evaluate the situation in realistic circumstances. And so use -1, negative, implying that it will be an exponential decay, and 0.1, which is just an arbitrary number, but in this case is to just represent that the rate of change is decreasing. And so yeah, he uses once again separation variables, um, integrates and takes a, because this function right here does not tell us much, so he um, finds the natural log of each function and comes up with this variable. And same as before, you go to the same process. So negative e to the negative 0.1 t plus c is the same as e to the negative 0.1 t times e to the c, and e to the c can be changed into a variable. And essentially from here, when you evaluate the function at 0 at 1 with 170 with the temperature at 170, you find out the initial temperature or the temperature of change is 100. And so from this, you found your exponential decay function, uh, which, yeah, that's about it. And so from this equation, Tom wanted us to evaluate the basically the half-life. Whoops. Basically the half-life of the function. I mean, of the cookies from this video that I just discussed. And so essentially, we're wondering how long the time. What is the time until the temperature? The time. Okay, we want to find the time until the temperature difference between 170 and 70 is halved, and then furthermore, 170 and 95. And so this property is showing the half life of the function. And so we were discussing earlier that we can actually, Alex, could you pull up a whiteboard?
Yeah, sure.
So our function is h of t
Hey, hold on, let me
equals.
grab my pen. Sorry.
No worries.
Um,
Equals 70 plus 100. Oh wait, 70. Not d. Sorry, 70. Right, 70 plus 100 e raised to the negative 0.1 t. Right. Okay. So this is the function to be able to find. Uh, so we can. Okay. So our thinking was that we know the temperatures that we're trying to achieve, and so we know this is essentially the rate of change throughout the entire cooling of the cookie. And so if we could just plug in variables, we're able to find, because our intention is to find, as you said, the time until the temperature is different. And so we were thinking that if we like I said, if we plug in the variables of the basically the milestones that we're trying to achieve. So like the temperature that um, we're trying to. So if we substitute HFT, because HFT equals temperature, for 120, we are able to find a rate of change at 120.
So basically, here T is time, and
Right.
and temperature is a function of time. So we're trying to find how long it takes for the temperature difference to half. So our goal here is to solve for T. Um,
Right.
so for the temperature difference to half, we're going from 170 down to 120. So we would plug in 120 for h of t. So h of t on the left side is going to equal 120, and then we're going with that. We're just going to use like arithmetic rules and just try to solve to
Right.
isolate the t and figure out what the t is.
Mhm. Okay. So subtract 70. We're solving for t, which is 50. divide by 100, which was a half. And we essentially have this function in which we can take the natural log of each function. And then essentially divide that negative point, negative 0.1, but let me find out what ln of a half is anyway. Sorry. Divide by, what is it? Negative 0.1. It equals 6.93 etc. So like 147, 93147. Okay, so is this in hours or is this in minutes?
I don't know if we know the units for this. It's just 6.93 units, I guess, because we don't know if it's like seconds or like minutes.
Right. So this is the change. I mean, this is the time it takes for the
So theoretically speaking, then, if we plug it, but it wouldn't really make sense. Would that make sense? I mean, theoretically speaking, the halftime is supposed to be the same, right? So if we plug in the other numbers, if we plug in 95, 82.5, we should theoretically get the same t.
Oh yeah, exactly. So we can,
or at the very least, it would be double. It would be a multiple of the 6.9. You know.
Right,
So
because
for it to have twice, we would need 6.9 times 2.
Right,
units of time
exactly.
passed.
Yes.
So theoretically, that's how it works. So we could try to just do one more just to prove that.
Right.
So basically,
yeah.
if we want, we can do the same thing again, but then instead of 120, we plug in 95.
Okay. I got you.
Yeah, it looks right.
Yep, 13.86294 relatively.
Yep, and I guess that's it. That proves it, because that's just doubling of what our first t was.
Right. And so
But
we
it's
know
13 point what?
sorry, 86294.
Okay, cool.
All right, cool.
Sure.